Hello everyone, today we're talking about neural networks and decision trees. I have Alexander Mattick with me, who is, maybe you want to introduce yourself.
Yeah, I'm currently a student at FAU, so in Germany, and most people don't know me probably through Yannick, through his Discord, where I'm one of the people who manage the paper discussions every week and present more of the theoretical papers usually.
So we came across this paper all across social media. I saw it at one point and I'm like, meh. And then I saw it like all over LinkedIn being like, whoa, neural networks are no longer a black box. We now know what's going on. I saw it on Twitter. I saw it essentially like it like really got some push behind it. As I said, when I first saw it, it was like, nah. This has been known for a while. So what does this paper say in a general sense? And has it been known for a while, or is there actually something in there?
Okay, so basically what this network does is, what this paper does, it shows how you can basically take a neural network, which is like a sequence of weights with nonlinearities in between, and then you can kind of iteratively rewrite them by effectively pulling out the right slopes and merging them up into new weights. And that would give you effectively this kind of structure.
It's important to say this is only for if the nonlinearity is piecewise linear. For example, a ReLU nonlinearity. Otherwise, we have an approximation, but this is actually an exact mapping that we're doing right here. So we just rewrite the neural network somehow, and then we get out what?
So we get out such a tree, and effectively you can see these W hats here, and these W hats, I think they're defined somewhere, I think somewhere up here. Yeah, effectively just unroll the piecewise slopes always from the layer above. So effectively we go and we draw the different cases that happened through the previous layer, we draw them up into the subsequent weights. And that gives us kind of this tree structure, because we of course get this unfolding of kind of which path can we go in the neural network, and then the next layer can kind of enhance in that path and so on.
I think it's still a bit unclear maybe to some people who are not super familiar with this. They might be under, like, the general notion is a neural network is a non-linear function, right? Therefore, I wouldn't just be able to represent it with a single, even if the W and the W hat are different, right? I still, at the bottom here, I see, X times W something, which is a linear function. So why all of a sudden I have a neural network? Why do I arrive at a bunch of linear functions?
This mostly has to do with the fact that neural networks intrinsically are just compositions of these piecewise linear functions. For example, there's been more recent work, I think here, in the spline theory of deep learning.
So more recent work. More recent than the paper we're looking at?
No, recent in the sense of it was published after 2000.
Okay.
This is a paper from, I think, 2018. And there they make this very, very explicit, where effectively they show that you can unfold almost every network into what is called splines. And you can think of splines as kind of regions, which then in and of themselves are affine linear. So it's a linear transform with some bias against it. And these deep neural networks are just different regions, all of which have their own slope and bias.
If we imagine a neural network with ReLU nonlinearities, if we imagine a point somewhere in the input, if we move that point like just a tiny bit, then we move it small enough so that it crosses none of these boundaries. A ReLU is essentially like this, so it has like a boundary here where the slope changes. But if we move just small enough that either the signal is in the slope, so it changes a bit in the slope, or it doesn't change at all because it's in the zero part. So if we move just a bit, we don't change the ReLU activation pattern. And that essentially means, since all the functions are either linear or piecewise linear, but we don't switch the piece, that means that within such a ReLU cell, it's essentially a linear function. I think that's what we see here at the end of the decision tree. The decision tree essentially says, with this particular input, which of these ReLU cells am I in? And inside of that cell, it's actually a linear function. And that's what's described here. The neural network in total is non-linear, because obviously we piece together super many of these tiny ReLU cell regions, and that can make something that appears almost like smooth, like because if we zoom out, then it's like a video game where everything is made of triangles, but you zoom out and it kind of looks round, it kind of looks smooth. The paper shows you can rewrite the neural network and you get something like this. What does it mean?
That's an entirely different question, because there are many different ways of viewing such a conversion. One is through a practical lens, another one is from a lens of what does it help us to study decision trees, another one is how does it help us to study neural networks. From a position of studying decision trees, it doesn't really help us that much, because neural networks are inherently a lot more impenetrable than decision trees. Really studying a neural network and that helping us to figure out something about decision trees is rather hard. Additionally, we have the problem that decision trees so the decision tree learning algorithms we build they themselves don't map to neural networks perfectly. What I mean by that is you can take a decision tree, like this thing here, and transform it into a neural network. However, during the decision tree training process, what you usually do is you take one of those effectively edges, and then you split it up into two lower ones. And for that, you may need a new neural network, because the capacity of the original one doesn't work out anymore. So from a perspective of taking a neural network and then helping to figure stuff out for decision trees, it's pretty hard. On the other hand, we can use these decision trees to figure out stuff about neural networks. This is a lot more promising, but there is often the case that to do the kind of analysis you can do with the decision trees, you don't necessarily have to explicitly build this tree, like the spline theory of deep learning paper, which does lots and lots of analysis. So for example, there was a recent paper which specifically looks at what batch norm actually does through this lens. But they don't need to build the explicit decision tree because they are just interested in this piecewise linearity. They're not necessarily interested in how exactly this fits to the actual neural network part or the actual tree part. And then last but not least, we can also analyze it through the view of, let's take an existing neural network like a ResNet and try and make it more interpretable. So that's where I also saw a lot of the hype going on, because decision trees are more interpretable. You could obviously go and take a ResNet, transform it into a decision tree, and then have this great interpretability. But in practice, this doesn't really line up that well. And the reason is, again, kind of connected to this idea of decision trees being small and then progressively growing, while neural networks are large and just basically large enough to fit everything inside of them. That means that the actual size of these neural network trees can become rather gigantic. The way we can do analysis with a theoretical lens is by studying something called the VC dimension, or the Vapnik-Chevonenkins dimension, which effectively just tells us how many different points can a network distinguish, which of course for a decision tree, if you have a fully balanced tree, like this one, would be 2 to the power of the depth of the tree, while for a neural network, it's a lot harder to figure out because you have all of these different architectures. What you can do though is we can go and we can bound this, and there's been lots of work in trying to figure out bounds. So for example, the best bound I could find is from this paper from 2017, which provides nearly tight bounds. And specifically, they provide this kind of theorem for a lower bound, meaning what they basically show is there's some universal constant which has this constraint. So effectively, the square of it has to be less than the number of weights. You get a minimum amount of regions of resolution from a neural network of W, so the number of weights, times L, which is the depth of the network, times the logarithm of W over L, and then you have this C constant in here. So it effectively means the number of regions we have scales a little bit more than linearly, because we have this W in the log, and it stays a little bit less than linearly with the number of layers, because we divide by L here. So if we now take this absolute lower bound, so what we can say is, because we divide by C here, we can just set W equals to So we can just set c squared equal to the square root of w, because that's kind of the worst case scenario. It gives us the smallest bound. And we can try and run this. So I have here this very trivial neural network, which has one hidden layer. We go from 1 to 1. So like this. Or we can also look at something like 1024 to look at something that would happen, for example, in a transformer, where you have these individual layers. If we run this, we get, for this relatively small network, we get a depth of this full decision tree of about 16. If you would try to plot this, so this is now going to run for a very, very long time.
I mean, 16, it doesn't seem that much, but this is essentially an exponent. This is an exponent. So it is a giant number.
Yeah, we have 2 to the power 16. Again, I'm taking here I'm rounding the depth down. 2 to the power 16 different regions, which is going to crush most algorithms. Even if you could build such a decision tree, so actually build one, it becomes rather hard to reason about them. Simply because the reason neural networks are hard to interpret is not necessarily because each individual component is hard to interpret. It's because the emergent properties of putting all of these things together, and these billions of parameters or millions of parameters even together, that makes the problem hard.
Yes, and I was so just to say that this 16 depth tree, that's kind of the best case scenario, right?
Yeah.
That's our bound on what would be possible in order for transferring a neural network to, like, what's the minimum size of tree we need to even represent that. It could be the case that it's more, but that was my impression as well, is when I look at a decision tree, I have sort of one path to go down to make the decisions by, right? But if I look at a classification problem, it's not always one path. It's not just, is the picture bright or dark? Well, okay, if it's dark, is it this and this? At some point, you get the same question, right? Is the picture bright or dark? Yes. Is there a small or a large object in it, let's say? This question you might want to ask whether it's light or dark. So you have like a matrix, right? Light picture, big object, light picture, small object, dark picture, and so on. But these are represented by 2 different nodes in a decision tree. No matter how you structure it, you have to ask one question first and the other question later. And that means one of these questions is necessarily going to be represented by 2 different nodes in the decision tree. And so that, just for me, looking at the decision tree, I no longer notice, I no longer recognize, or the algorithm doesn't anymore tell me that these 2 things are actually related in some way. So whereas in a neural network, I have internal representation, I have features or weights that look at particular features inside of these representations. One set of the neural network might look at the lighting condition. The other part of the neural network may look at the shape of something, and they can work in parallel. In a decision tree, it's one after the other, and therefore the analysis gets way harder because stuff in the decision tree happens everywhere, and no algorithm can tell me, by the way, these things represent the same feature.
It kind of boils down to this fundamental tension between having parametric and non-parametric approaches. Because, for the people who don't know, the distinction here is effectively a neural network is a fixed skeleton with lots of blank spaces, and the objective of fitting the function in that neural network is figuring out what should be put into its blank spaces. This is a parametric approach because we have lots of parameters. Decision trees are non-parametric approaches. So what you do is you effectively say we have this entire family of different trees which not only have parameters like this W, but also you have effectively the architecture which gets optimized along the way. And if you have non-parametric approaches, this usually gives you way different classifiers. Because in a parametric approach, because we have stuff like gradients, which make a lot of sense in parametric approaches, you can say something like, I don't necessarily want an optimal split, I just want some split. That effectively amounts to, you go and you take this W and just move it around a little bit to go to go closer to a good split. Where decision trees do it a lot differently, because decision trees have to work with this gigantic family of functions. We now have to do optimal splits, at least to some optimality constraint, because you just randomly kind of pull out decision trees and try to figure out, is this the right decision tree? You're never going to be able to finish. This is also why decision trees tend to work well in stuff like tabular datasets, because you have relatively few features which are very well defined, and you can compute statistics for them, which help you to figure out what would be the perfect split for a specific feature, and which feature should I split next. While for something like an image, think about it, you have an image which is 224 by 224 by 3 RGB channels. The statistics you can get even with a massive dataset are not that great, especially since you have to consider things like shifting around the image a little bit to basically make the statistics more robust. And that means it's very hard to fit a decision tree because the statistics are always bad. A neural network performs way better because it doesn't care about how well it splits. It just does some split and hopes for the best. This means that a neural network is by its nature going to be less optimal, but it's also going to make some progress even if there are only very bad statistics, where a decision tree always has some sense of optimality if you fit it with something like cart, because you only do somewhat optimal splits. Of course, at the cost of you have to have some notion of what optimal means, so you have to know, so you need those statistics.
Yeah.
And something like this algorithm, it is a decision tree, so it's what one would call a simple function in like mathematical speak. So decision trees are effectively just nice representations of simple functions, but it's not really a decision tree as it would be produced by a decision tree algorithm. And that's the problem what makes them uninterpretable, because they just grow without bounds, these neural network trees.
So when we look at, let's get like back to the paper at hand. By the way, this is still running, which I like. Back to the paper at hand. Is the proof sound? The proof that neural networks are decision trees, right? It's like it is absolutely sound. It's not wrong. All good. Is it new or unknown?
No. So there are multiple things to that. One is there are already papers in the past which did that. So for example, this paper I think is from 1999. Yeah, November 1999. They also showed like algorithm for extraction of decision trees from artificial neural networks. So this is known. And it's also one of those things that oftentimes just happens to plop out as a corollary. So there are very few people who go and explicitly write this proof down, because it's kind of a natural thing that occurs. If you have some algorithm which splits the world up into kind of classification polygons or simplices or affine regions, which, for example, this paper does, then getting this decision tree form is effectively just a corollary. It just plops out passively. So this paper here, for example, the spline theory of deep learning paper, could easily just say, well, yeah, the decision of which spline we are in is made hierarchically in the form of a decision tree. So it would be a one sentence, and that just plops out. The same would be true for many of these theoretical proofs, where, first of all, very rarely do you actually need this decision tree kind of realized, but oftentimes the proof behind it that, for example, abuses the fact that we have this ReLU max function, which effectively tells us to go either to the left, where you have this zero region, or to the right, where we have new values. That is often just there. You don't need to do any more to get the actual decision tree out.
I know this from because I used to work quite a bit in the field of adversarial examples, and there I think it was made oftentimes quite explicit to some degree, because obviously people, as long as stuff is linear, you could have some kind of bounds on how worse it can get. But then as soon as it's non-linear, it gets a bit more tricky. And you've also shown me before like a paper on verification of neural networks, which is exactly right. Yeah. Sort of in this area where people are trying to say, well, how bad can it get? And they use the fact that also their we have these essentially these cells of linearity.
So one of the problems, it's also what this reloplex algorithm, the idea is that you can view this max operation effectively as splitting everything up into a simplex. Then you can make arguments about, with something like an SMT solver, you can try to make arguments, okay, what happens inside the simplex, or basically what can happen inside the neural network. And you can do that to guarantee some safety, to have some safety guarantees. But even this algorithm gets crushed at scale, and the scale, as we've seen here, I think it's still running, yeah, it explodes rather quickly. So, and they of course don't explicitly build this, but yeah, this idea of neural networks mapping well to decision trees kind of boils down to the fact that a feed-forward network is effectively just a gigantic graph. You can just take you can effectively compute the spanning tree of that graph, and that gives you a decision tree, at least in the case of a ReLU. And that's basically also what this paper does. We compute the spanning tree by computing these W hats, and these W hats take the slope from take the appropriate slope from the previous layer, and then build up the appropriate W hats.
So maybe for people, so we can just go to these formulas with one of the A's, because that's kind of the crucial part of the math right here, is these A vectors, and you have to, like, it still seems a bit like magic. We have like the nonlinear composition of function, and then all of a sudden, boopity boopity boop, we have these A vectors, and somehow now all is linear. But one has to remember that. So on the bottom here, we have the nonlinearity. Essentially what I do is I take the signal that comes through the network and I look at the signal at the nonlinearity, and there I say, well, where is the signal such that the ReLU is active, and where is the signal such that the ReLU is inactive, and I just replace that by a vector of ones and zeros, or the slopes and zeros, right? But these vectors are dependent on the signal, and that's why they're going to look different if the input is different, and that's why it's a linear function for a given input in a given very tiny circle, right? So I think that's the connection. Now, the paper also has some experimental result, and there is a small claim, but there is a claim that the decision tree representation might be advantageous in a computational manner. So they have a table 1 comparing the decision tree and the neural networks for the same function in terms of their computational complexity. So it turns out the decision trees have more parameters, which is odd for a non-parametric function, but I guess they're not learned parameters. Yet the neural networks use more multiplications and additions than the decision tree. What do we make of that?
Well, computation often is not the same as computation, because you may have more multiplications or additions, but they may be in a form which is just nicer for you to work with. So, for example, if we look at the trees, or like here, or let's go back up to this kind of prototypical tree, where effectively we have these multiplications with this x0 input. What happens is that we do have fewer multiplications using that structure, because effectively we abuse the fact that we don't have to compute the entire matrix. We only have to compute the part which is actually going to be relevant for us later on. That, of course, reduces the number of multiplications. But on the other hand, we now have this spreading out. We have more decisions in here and less multiplications. And depending how your hardware ends up, it might be that basically paying for more computation and having less decisions is better. That's why training a decision tree on a CPU makes more sense than training it on a GPU. On the other hand, there are also approaches which take decision trees and basically compile them into what's effectively binary matrix multiplication. These algorithms tend to, of course for inference in that case, but these algorithms tend to be a lot faster, simply because even though you do more addition and multiplication and stuff like that, you end up having so much parallelism that this, what is it, a factor of 4 roughly, is not that meaningful, or it's more closer to 3.
Well, on the left it's 8, but it's 2 versus 16. Well, in any case, but that's the point, right? If one were to actually implement the decision tree on like a GPU, one would actually regain all of these multiplications and additions, because it just makes more sense to put the binary vector there with a lot of zeros and then multiply all of these zeros instead of trying to mask out stuff, and because the GPU can just parallelize so hard.
Yeah, it's mostly that GPUs don't tend to do well with lots of decision making and lots of sparsity.
Yeah.
Because just of the way they are designed. They're designed to do large operations on a lot of data very basically monotonically. They just do kind of a large matrix multiplication with very little decision making. Every single one of these thousands of CUDA cores effectively does exactly the same thing. And that then gives you kind of this boost, because you have thousands of cores doing very simple, very repetitive actions. And if you have more decision making, if you have more decision making in there, that just makes it slower.
I think I interviewed Nir Shavit of Neural Magic, and effectively they're doing something very similar, where they say, okay, what we do is we take like a BERT or something like this, we prune it very in a special way, such that the rest is something we can infer on CPU really well, which is essentially like very similar to this paper right here. So the idea of sort of pruning it down, and all of a sudden you may end up with something that's sparse, requires more if else, but then is very much suited to a CPU. If we think about maybe the last question for today, if we think about okay, this paper is it's certainly correct and all, but we think it has been known, or it's I don't like the word trivial, because nothing, like I used to hate that as a student, because to me nothing ever was super trivial, and it's, even if it's trivial, it's good that it's written down explicitly somewhere, right? You can point to a place or here, but in a sense it is like something that a lot of people have just kind of done on the side, because it is fairly like a natural outcome of working with these systems. But if we look at a bit beyond that and say, is there a way in which decision trees can kind of make a bit of a comeback in today's world of deep learning? Maybe not as a substitute, but as an augmentation of neural networks. Can we, like, what kind of properties does a problem need to have such that a combination of something like decision tree algorithms, like decision tree learning algorithms and neural networks are the best?
So decision trees really like to have these very, very well-defined statistics, because that helps them to do their splits. Effectively, neural networks scale with gradients, so if you can't get gradients, you have a hard time, and they also scale with size, simply because, as we've seen here, you just get more possible, more representational power. So it's just better. You can effectively simulate a small decision tree inside a large enough neural network by just setting everything else to 0 around it. The trick that makes decision trees work well is if you have these statistics. So that's why decision trees work incredibly well on something like tabular data. Like, you can also do tabular, like, deep learning, but that's probably like you're going to do research, you're going to do probably a PhD, and then out plops a project which may or may not be competitive on tabular data. While on the other hand, I can just use XGBoost and get great results right now. What you would want to do to get decision trees to work well is you would want to take these very, very high dimensional, these very, very information sparse, for example, images, and transport it into like a lower dimensional space where you can then get the statistics. So for example, if we have a two-stage approach where you have main neural networks inferring different features of the same thing. So you first try to classify whether or not it's a cat or a dog, then you try to classify, I don't know, its size or whatever, and you put them all down, then you can start doing a decision tree learning, and the decision tree is probably going to be a lot more performant simply because you get this smaller size through the fact that the decision tree is much more optimal in how it uses its splits and capacity.
It seems like the current wave of self-supervised learning might actually be a good candidate to build something like this on top, because the self-supervised algorithm, they tend to sort of extract many different kinds of features, whereas like if I pre-train a classifier on ImageNet, let's say, that classifier is going to be attuned to very few features for the bunch of classes it needs to classify. But just from what I can observe, the self-supervised approaches, they just tend to kind of get this rich representation out of images, and we see that if we look at anything that uses a VQGAN encoder nowadays, which is almost all of the AI art projects. So they're so rich, such a rich representation. So this could be, especially maybe the quantized stuff, could be like a very fertile ground to then put like decision trees, random forests, whatever on top of that.
Yeah.
Cool. All right. I think that's about. The paper is kind of really short. It's, I guess, four or 5 pages. If you it is very, like, I think it's very approachable. So if you've never heard of any sort of equivalence like this or any math in this area, it's very helpful, I think, to actually look at it and just see how it's done. Might give you a bit of an insight. And yeah, Alexander, thank you so much for being here. It was a pleasure.
Yeah. Thank you for having me.
Cool. And everyone, if you want to hear more rants of Alexander and myself, we have discussions on Discord almost every Saturday evening. Well, in at least evening in Europe. Right. Cool. Bye, everyone.
Bye.